Hi, this is the screencast for section 4.5 to 4.6. Section 4.5 is on stoichiometry. So the learning objective is explain changes in the amounts of reactants and products based on the balanced reaction equation for a chemical process. So stoichiometry, it's a lot of math, a lot of conversions. So the essential knowledge is you want to be able to do stoichiometry problems of any sort, including gas stoichiometry and solution stoichiometry. So over here, I just have a roadmap just to show some of the conversions that you might have to make. This step right here, the mole to mole conversion, that's going to be in every type of stoichiometry problem, no matter what. And that includes using the mole ratio to convert from moles of your starting substance to moles of your ending substance. And the mole ratio, we just get that from the balanced chemical reaction, the coefficients in the balanced chemical reaction. And then either at the beginning or at the end, we might have to make a mole conversion. So if we're converting between moles and mass, in that case, we want to use the molar mass of the substance. If we're converting to particles or from particles, we need to use Avogadro's number, 6.02 times 10 to the 23rd. And a particle could be an atom, could be a molecule, could be a formula unit, could be an ion. And then if we're converting for volume, if we want to find liters, there's a couple different ways you can do this. If you're at standard temperature and pressure, then you can use the relationship that there's 22.4 liters of gas at STP per mole. And we can use that as a conversion factor to go back and forth between volume and moles. But if you're not at standard temperature and pressure, then we can just use the ideal gas law, PV equals nRT. To go from moles, which would be N, into volume, which would be our V right there. So that's the gas stoichiometry part of it. And then solution stoichiometry, that's using molarity, where if we know the number of moles, molarity is moles divided by liter. So if we know the number of moles and we know the molarity, then we can convert to liters of a solution. This is an example of a stoichiometry problem worked out. And this is just a three-step mass-to-mass conversion where we have a given mass of a substance, in this case 6.50 grams of aluminum. And then we want to find grams of aluminum oxide. So we're starting off with the given quantity, and you set up conversions, and we should be pretty good at mole conversions at this point. But when you set up conversions, it's always whatever units you are given, we want those units on the bottom of the conversion factor so they cancel out, and we find some other units. In this case, we're going from grams to moles. So it's always the desired unit over the given unit so that we cancel them out as we go. But this would be the conversion from grams to moles right here. This step right here, this is our mole ratio. And 2 and 4 come from the coefficients in the balanced equation. That's the mole ratio. Then this is the molar mass of this aluminum oxide. That's what we're looking for. And then we just do the calculation. Down here at the bottom, it shows you how to work with the numbers. You multiply by any numbers on top of the conversion factors, and you divide by any numbers on the bottom. Next, we have 4.6, Introduction to Titrations. So the learning objective here is identify the equivalence point in a titration based on the amounts of the titrant and analyte, assuming the titration reaction goes to completion. So the essential knowledge here, we want to know the titration procedure, and we've done a couple of these, but just to review, this thing right here, this is the equipment. This is called the burette, B-U-R-E-T. And we use a ring stand and a burette clamp, and we set up this burette, and we, in the burette, you have the titrant. That's the solution that goes in the burette. It's called the titrant. And down here you have the Erlenmeyer flask, and we use the Erlenmeyer flask so we can swirl the solution as we go. And the solution that's in the Erlenmeyer flask is called the analyte. So down here it's the analyte, and up here the solution is the titrant. And then you also want to know some of the basics about the procedure, as in at the beginning you rinse the burette with distilled water completely, and then you rinse it with a small amount of the titrant, and then you fill up the burette with the titrant, remove the air bubble, and then you measure the starting volume and the final volume, and then you can do calculations after that. So those are kind of the basics right there. Then you also want to know the equivalence point. The equivalence point, if you're to graph out, this is a titration where you're starting with a base and you're titrating it with an acid. The equivalence point right here, it's the point of inflection on the graph right there. And you want to know that the equivalence point is based on stoichiometry. It's when the analyte is totally consumed by the titrant, and you can do a calculation to determine that. But right there, it's shown right there, that point of inflection on the graph. And you also want to know what the endpoint is. That's another piece of essential knowledge. Now, the endpoint is based on observations, whereas the equivalence point is based on stoichiometry and calculations. The endpoint is based on an observation in the lab, like an observed change. And usually we use an indicator in a lab that will change color. It'll be one color in a base, a different color in an acid. And the point at where it changes color is called the endpoint. So again, the equivalence point is it's where the analyte is totally consumed by the titrant, and the endpoint is the observed change in the lab that shows that. And that's it for today. Have a great day. Bye.